Hi guys, welcome to the official iMath YouTube channel. Sir D at your service. Before we start, let me check the attendance first. And as customary in all my classes, all you need to do is to answer the question of the day to signify your attendance. But because we do not have physical classes, no physical attendance folders, you may write your answer in the comment section of this video. Okay? So our question of the day was submitted by a classmate of yours na itago natin sa pangalang Eman Puti. His question goes like this. Kung meron kang food coloring at papalitan mo ang kulay ng kwek-kwek, anong kulay ang ipapalit mo at bakit? Okay? Anyway, let us now proceed to lecture 20 of Math 22. Here we discuss the 6 basic types of quadric surfaces. And I am going to divide the video into 2 parts. For the first part, we consider the 4 central quadric surfaces. And for the second video, we look at the 2 non-central quadric surfaces. But what is a quadric surface? A quadric surface is the graph of an equation in the 3-dimensional space, which can be written in the following general form. So we have here terms of degree 2, terms of mixed variable, terms of degree 1, and a constant term j. Here, the coefficients a, b, and c should not be all 0. That means at least one term must be of degree 2. But in fact, for the 6 basic types of quadric surfaces, at least 2 terms are of degree 2. The presence of a term with mixed variables indicates a rotation at an angle which is not equal to 90 degrees. And that is already out of the scope of the course. Hence, we will be considering only equations of the following general form. Observe here that this constant term j may either be 0 or non-zero. In the case that it is equal to 0, we have the following equation. In the case that j is equal to a non-zero constant, then we can divide both sides of the equation by that j so that the constant term will be 1, and we can place that 1 in one side of the equation, and we get an equation of this form. So these are the standard form of the equation of a quadric surface. Our goals for this lecture are 1. To identify the type of quadric given its equation, and 2. To sketch a portion of the quadric that sufficiently shows its behavior or shape. Let us now look at the first type of the central quadric surfaces. The first type is called an ellipsoid, and its standard equation is given by x squared over a squared plus y squared over b squared plus z squared over c squared equal to 1, and whose illustration is shown in the figure. Let us make relevant observations on this equation to determine what properties of the equation tell us that this represents an ellipsoid. First, notice that all 3 variables are of degree 2. Moreover, all of them have positive coefficients. And finally, the constant term is 1. So when all these 3 conditions are satisfied by the given equation, it represents an ellipsoid. Let's proceed to the graph of the ellipsoid. Here you have a shaded graph for easier visualization. But when you are asked to draw an ellipsoid, a skeleton or a frame for the ellipsoid will do. Observe here that I actually have 3 ellipses drawn on the surface of the ellipsoid. We have the traces on the 3 coordinate planes. You can see here the trace on the xy plane, the trace on the xz plane, and the trace on the yz plane. Those 3 ellipses would be sufficient for a skeleton of an ellipsoid. Let us take a look at a particular example. Consider x squared over 9 plus y squared over 16 plus z squared over 4 equal to 1. This equation definitely represents an ellipsoid because we can see here that all variables are of degree 2, all of them have positive coefficients, and the constant term is equal to 1. So to sketch the graph of this ellipsoid, we just identify the traces on the coordinate planes. Let's begin with the trace on the xy plane. Recall that the xy plane has equation z equal to 0. So all we have to do here is to replace the variable z in the equation of the ellipsoid by the number 0. And when we do that, this term vanishes, and that will leave us with the following equation. A sum of two squares of the variables equal to 1 represents an ellipse. And here, the ellipse is centered at the origin of the xy plane. And we can use the 4 points located on the coordinate axis to draw the ellipse. In particular here, on the x-axis, we measure the root of 9, that is 3. So 3 from the center towards the positive direction of x, 3 from the center towards the negative direction of x. Also, on y, we measure the root of 16, that is 4. So 4 units from the center towards the positive direction of y and 4 units towards the negative direction of y. Using those 4 points, we have this ellipse on the xy plane. Next, on the yz plane, whose equation is x equal to 0, we are going to get the equation y squared over 16 plus z squared over 4 equal to 1. This represents another ellipse, but this time the ellipse is located on the yz plane. The center is the origin of the yz plane. We measure square root of 16, that is 4 units along y. So 4 towards the positive direction of y is here, and 4 towards the negative direction of y is here. We measure the square root of 4, that is 2 units along z. So 2 units on the positive direction of z and 2 units on the negative direction of z. So using those 4 points, we get this ellipse on the yz plane. And finally, on the xz plane, whose equation is y equal to 0, replacing y here by 0 will give us the equation x squared over 9 plus z squared over 4 equal to 1. And this is an ellipse located on the xz plane with center the origin of the xz plane. We measure root of 9, that is 3 units on x, which we actually have here. So this point and this point. And the square root of 4, that is 2 units on z. So we have this point and this point. So using those 4 points, this is the ellipse located on the xz plane. This is an enough skeleton for the ellipsoid with the given equation. Now for easier visualization, I am shading the surface and observe that after shading, I have now some portions which are broken. We use broken curves or dashed curves to indicate that a portion cannot be seen from your perspective, from the front of the surface. Okay. Finishing touches, I have here labels of some important points of the ellipsoid. Before we proceed to the second type of the central quadric, let me have some remarks on the ellipsoid. It can happen that all 3 denominators of the ellipsoid are equal. Multiply both sides by a squared, it will give us x squared plus y squared plus z squared equal to a squared. And recall that such equation represents a sphere centered at the origin of radius equal to a. Now what happens when 2 of the denominators are equal? Then what we can do is compare the third denominator with those 2 equal denominators. The third denominator may either be smaller or larger than the 2. In the case that it is smaller than the 2 equal denominators, the ellipsoid becomes an oblate spheroid. In the case that the third denominator is more than the 2 equal denominators, the ellipsoid becomes a prolate spheroid. Let me show you an illustration of an oblate spheroid and an illustration of a prolate spheroid. Please do not get confused that when I rotate the prolate spheroid 90 degrees, I will get an oblate spheroid. That is not the case. So to differentiate between an oblate spheroid and a prolate spheroid, let me give you particular examples of these surfaces. For an oblate spheroid, we can consider the shape of the Earth, for example, at least for non-flat earthers. Or it can be the shape of a Mentos candy. On the other hand, an example of a prolate spheroid would be a football, the American football, or it can be an egg. Okay, so that is how an oblate spheroid differs from a prolate spheroid. Let us now consider the second type of central quadric. It is called an elliptic hyperboloid of one sheet. Its standard equation is x squared over a squared plus y squared over b squared minus z squared over c squared equal to 1. For this particular form of the equation, the graph of the elliptic hyperboloid of one sheet is illustrated here. Again, let's make relevant observations on the equation of the elliptic hyperboloid of one sheet. First, we can see that again, there are three variables of degree 2, but unlike in the ellipsoid, there is exactly one coefficient which is negative. The constant term, however, is still equal to 1. Let's proceed to the graph of the elliptic hyperboloid of one sheet. For the graph here, we can consider the traces on the coordinate planes. Observe here that the trace on the xy plane is this ellipse. The trace on the yz plane is this hyperbola. And the trace on the xz plane is another hyperbola. So the traces consist of one ellipse and two hyperbolas. This actually gives us an idea how the name of the quadric surface is obtained. The more dominant trace takes over the noun part of the name, that is the hyperboloid, while the other trace takes the adjective part of the name, that is the adjective elliptic. Hence the name elliptic hyperboloid. Now, these traces, when drawn in the space, as you can see, are drawn around the z-axis. So we say that this particular quadric surface is actually axial, okay? And in this particular equation and graph, the axis of the surface is the variable associated with the negative coefficient. Now observe that this surface can actually extend infinitely towards the positive z-axis and towards the negative z-axis. However, in my illustration, I cut the surface by taking a plane parallel to the xy plane above the xy plane and another plane parallel to the xy plane below the xy plane. In other words, we cut it by two planes perpendicular to the axis of the elliptic hyperboloid of one sheet. And observe here that the intersection of the surface with those two planes are two ellipses. So for the skeleton of the elliptic hyperboloid of one sheet, the necessary traces are two hyperbolas and three ellipses. As a tip, when you're asked to draw an elliptic hyperboloid of one sheet, you may draw the three ellipses first. Again, these are located on planes perpendicular to the axis of the elliptic hyperboloid. And from there, you can easily draw the two hyperbolas by connecting corresponding important points on the three ellipses. Before we proceed to the example, note that this given equation is just a form, meaning there are other orientations for this elliptic hyperboloid of one sheet. In fact, this negative sign can commute. It may be located on the y variable, or it may be located on the x variable. In those cases, then these axes are actually interchanged, or the quadric is actually rotated 90 degrees. Let me show you the illustrations. So here we have an elliptic hyperboloid of one sheet, and as you can see in the illustration, clearly the axis is the y-axis, where the negative sign is associated. Also, here we have an illustration of the elliptic hyperboloid of one sheet whose axis is the x-axis. That is where the negative coefficient is located. Now, if you would compare the three orientations, I personally do not want to illustrate this or this. I always want an upright illustration of the elliptic hyperboloid of one sheet. And if I want to illustrate this orientation, so instead of rotating the quadric itself, we are just going to relabel the axis. Okay? And to do that, we first label the vertical axis, and we always take that to be the axis of the elliptic hyperboloid of one sheet. Let's consider an example. Consider the equation x squared plus y squared over 4 minus z squared over 9 equal to 1. Here we can see that all variables are of degree 2, with exactly one of them having negative coefficient, and the constant term is 1. Hence, this represents an elliptic hyperboloid of one sheet. For the illustration, we have to choose the best orientation of the three-dimensional space so that the graph will be an upright elliptic hyperboloid. Observe that the negative coefficient is associated to the variable z, and hence the axis of this quadric is the z-axis. So we choose that to be the vertical axis, and here you can label the x and the y coordinates using the usual orientation of the three-dimensional space. Now for the necessary traces, recall that we need 3 ellipses which are drawn on planes perpendicular to the axis of the quadric surface and 2 hyperbolas. So for the ellipses, we can look at the trace on the xy plane and on 2 planes parallel to the xy plane. For the trace on the xy plane, we simply have to set the z-coordinate to 0, and when we do that in this equation, this term vanishes. It leaves us with the following equation. This represents an ellipse centered at the origin of the xy plane, and the 4 important points would be the points on the x-axis and on the y-axis. On the x-axis, we measure 1 unit, so 1 on positive x, 1 on negative x. On the y-axis, we measure the square root of 4, that is 2. So 2 on positive y, 2 on negative y. Using those 4 points, we get this ellipse. For a plane located above the xy plane or below the xy plane, we can take a positive value for z and its negative. In particular, let me take z equal to 3 and z equal to negative 3. Observe that if z is either 3 or negative 3, this will give you the same equation. So when you plug those values in place of z here, you can verify that the resulting equation in standard form is x squared over 2 plus y squared over 8 equal to 1. This represents an ellipse centered at the origin of each of these 2 planes. So in particular, for the plane z equal to 3, we start from this point and we measure the root of 2 units on an axis parallel to x. So from here, square root of 2 units towards this direction and square root of 2 units towards the opposite direction. In the same manner, you measure square root of 8, that is equivalent to 2 square root of 2, along the direction of the y-axis. So from here, 2 square root of 2 units towards here, and 2 square root of 2 units towards that direction. You do the same thing for the plane z equal to negative 3. The 2 ellipses will have the same size. Okay, so we get these traces. Now, once I have these 2 ellipses, the 2 hyperbolas can be easily drawn. So we need to get the trace on the YZ plane. That is when x is set to 0. Clearly, when x is 0, we get the following equation of the hyperbola. Then here you can see that when I intersect these ellipses with the YZ plane, the intersection would be these 3 points on the right and these 3 points on the left. Using those points, we have this hyperbola located on the YZ plane. Likewise, on the XZ plane, that is when I set y to 0, setting y to 0 here will give us the following equation of a hyperbola. And observe that if I intersect these 3 ellipses with the XZ plane, the intersection would be this point and this point on the x-axis. Draw an axis here parallel to x, we get a point here and a point here. And another axis here parallel to x, we get 2 points. Connecting corresponding points on these 3 ellipses, we get this hyperbola. So this is a skeleton for the elliptic hyperboloid of one sheet with the given equation. Let me shade so that you can easily visualize it in the 3-dimensional space. And again here, some of the portions are broken or dashed to indicate that they cannot be seen from your perspective. We label some of the important points in the elliptic hyperboloid of one sheet. Let us proceed to the third type of the central quadric surfaces. The third type is called an elliptic hyperboloid of two sheets. Its standard equation is given by this, whose corresponding illustration is shown in the following figure. If we make relevant observations on the equation and how it differs from the first two types, we can see here that all 3 variables are of degree 2. However, here, exactly 2 coefficients are negative. The constant term is still 1. For the graph, we can see that this quadric is also axial. It has an axis. In this case, it is the z-axis. And if you observe from the equation, the variable z is the only variable with the positive coefficient. Also here, you can see the traces on the 3 coordinate planes. The trace on the xy plane is nothing. The quadric does not intersect the xy plane, so it is empty. While the trace on the xy plane and on the yz plane are both hyperbolas. Now for the skeleton of the elliptic hyperboloid of two sheets, observe that these hyperbolas extend infinitely up and down. So I have to cut them by 2 planes, one parallel to the xy plane located above the xy plane and one below the xy plane. And so for the skeleton, we will be needing 2 hyperbolas and 2 ellipses, as you can see in the figure. And just like elliptic hyperboloid of one sheets, we draw the ellipses first to easily sketch the 2 hyperbolas. Please note that this is just a form for the equation of the elliptic hyperboloid of two sheets. There are the 2 possible orientations when you rotate this 90 degrees towards the y-axis or 90 degrees towards the x-axis. That means this positive sign may commute. If this is located on the y variable or on the x variable, then we have the following orientation. So here the positive coefficient is associated to x, so you have this elliptic hyperboloid of two sheets with x-axis as its axis. On the other hand, the positive coefficient here is associated to the y variable, so we have a graph whose axis is the y-axis. But then again, personally, I prefer illustrating the first orientation. Okay, and so to get such illustration, an upright elliptic hyperboloid of two sheets, we again set the vertical axis as the axis of the elliptic hyperboloid of two sheets. Let us consider an example. In this example, observe that all variables are of degree 2, with exactly one of them having a positive coefficient, and the constant term is equal to 1. Thus, this represents an elliptic hyperboloid of two sheets. Now, for the illustration, we choose the best orientation of the three-dimensional space. And here, observe that the positive coefficient is associated to the z-axis. And hence, we can use the usual orientation of the space. For the skeleton, we need two ellipses and two hyperbolas. Recall that those ellipses are located on planes perpendicular to the axis of the quadric. So we assign a constant value for z that is positive, and we assign another negative value for z. Okay, let me choose 4 and negative 4. If I plug in 4 or negative 4 in replace of z in this equation, you can check that the resulting equation is x squared over 27 plus y squared over 3 equal to 1. Well, this represents an ellipse centered at the origin of each of these two planes. Okay? If I start at z equal to 4, so somewhere here, we measure square root of 27, that is 3 square root of 3 along x. So from this point, 3 square root of 3 towards positive x, and 3 square root of 3 towards negative x. We measure square root of 3 along y. So from this point, square root of 3 units towards the positive y and towards the negative y. Connecting those 4 points will give you the ellipse on z equal to 4, and the ellipse on z equal to negative 4 will have the same size. Now for the two hyperbolas, we just need to find the traces on the xz plane and the yz plane. On the yz plane, we set x to 0, and when we do that, this term vanishes. That leaves us with the following equation. A difference of two squares equal to 1 represents a hyperbola. The vertices of the hyperbola are located on the axis of the positive or with the positive coefficient, particularly at point where z is equal to 2 and at the point where z is equal to negative 2. So 2 on z is here, negative 2 on z is here. So from this point, we draw the hyperbola located on the yz plane. We get this. And finally, the trace on the xz plane is obtained when we set y to 0. Setting y to 0 in this equation gives us the following equation of a hyperbola. This will be easier to sketch now because the vertex will also be here and here. And then we just have to connect each vertex with the vertices of these ellipses. We get the following trace. So this is a skeleton for the elliptic hyperboloid of two sheets with a given equation. Shading for better visualization, dashed or broken for portions which cannot be seen from your perspective. Labels of some important points in the graph. In addition to this, we can look at the trace on the xy plane, that is when I set z to 0. Observe that when I set z to 0 here, we get an equation where we have negative of a square minus a square equal to 1. Of course, there will be no values for x and y that will satisfy this equation. Hence, the trace is empty. And that is very evident in our illustration here. This elliptic hyperboloid of two sheets does not intersect the xy plane. The fourth type of the central quadric surfaces is called the elliptic cone. This is an equation of the elliptic cone that is shown in the figure. Let's make necessary observations on the equation. Observe that all three variables are still of degree 2. One coefficient has different sign. The constant term is 0. So this condition here makes it very much different from the first three examples. Also take note here, I mentioned one coefficient has different sign. I did not mention one coefficient has negative sign because you can actually multiply this by negative 1, and when you do that, two of them will have negative signs and one will have a positive sign. Okay, for the graph, this is also axial, and we can see that this illustration has axis, the z-axis, which corresponds to the variable with the different sign. The traces on the coordinate planes, we can see here that the only intersection with the xy plane is a point. The intersection with the xz plane is a pair of intersecting lines, and the intersection with the yz plane is another pair of intersecting lines. So we have these traces. Aside from these traces, to draw a skeleton for the quadric, we also need two ellipses. These ellipses are drawn on planes perpendicular to the axis of the quadric surface, just as how we did it for the elliptic hyperboloid of one sheet and two sheets. Take note that this is a form of the equation. There are two other possible orientations for the elliptic cone. You get that when you rotate this 90 degrees towards the y-axis or 90 degrees towards the x-axis. The effect in the equation is the variable with the different sign changes. This is the elliptic cone with axis, the x-axis, and you can see from its equation that the variable x has the positive coefficient. And finally, this is the elliptic cone whose axis is the y-axis, and from its equation you can see that the variable y has the positive coefficient. But then again, when illustrating elliptic cones, it would be best if you choose the orientation where the axis of the elliptic cone points upward. Let us consider a particular example. For this equation, we can see that all variables are of degree 2 with exactly one different sign, and the constant term is equal to 0. Hence, this represents an elliptic cone. For the graph, we want to choose the best orientation of the coordinate axis. So observe here that the variable associated with the different sign is the variable z, and hence we take the z-axis pointing upward, and we can use the usual orientation of the three-dimensional space. For the traces, well, we can start with the trace on the xy plane. That is when we set z to 0. Setting z to 0 in this equation will give us a sum of two squares equal to 0. And the only value for x and y that will satisfy this equation is when x is 0 and y is 0. So we get the point 0, 0, 0, or the origin. Now for the traces necessary for the skeleton of the elliptic cone, we want two ellipses and two pairs of intersecting lines. The two ellipses must be drawn on two planes perpendicular to the z-axis. So that means we have to assign a constant value for z, one positive and one negative. In particular, let me take z equal to 3 and z equal to negative 3. When I plug in 3 or negative 3 in replace of z here, you can check that the resulting equation is x squared plus y squared over 4 equal to 1. This represents an ellipse centered at the origin in each of these two planes. In particular, if this is z equal to 3, we measure one unit parallel to x, so one towards positive x and one towards negative x. And we measure 2 units on y, 2 on positive y, 2 on negative y. Using those 4 points, we can draw the ellipse, and the ellipse on z equal to negative 3 will have the same size as that. Now for the other traces, we consider the trace on the yz plane. That is when x is set to 0. When x here is 0, this term vanishes. A difference of 2 squares equal to 0, you can rewrite as y squared over 4 equal to z squared over 9, where you can take the positive or negative roots on both sides. So that will give us two equations. Y over 2 equal to z over 3 and y over 2 equal to negative z over 3. Both of them represent a line in the space. Hence, we get a pair of intersecting lines. So here, we have to take the intersection of these ellipses with the yz plane, yz. Observe that when I construct an axis parallel to y here, the intersection would be this point, this point, and this point. We connect opposite vertices to draw the pair of intersecting lines. We get this. And finally, on the xz plane, we set y to 0. And again, when we do that, it gives us a difference of 2 squares equal to 0, where we can write x squared equal to z squared over 9. Taking roots on both sides, we have either x equal to z over 3 or x equal to negative z over 3. So x, z plane, you construct here an axis parallel to x. The intersection points would be this, and here an axis parallel to x. We get this intersection and this. Again, you connect opposite points to draw the pair of intersecting lines. We get the following. So this completes the skeleton for the given elliptic cone. A shading for easier visualization with some portions broken. Again, to signify they cannot be seen from your perspective. Some label of important points on the graph. So that completes the lecture on central quadric surfaces. Please watch the next video where we consider the non-central quadric surfaces. Thank you.